Yes.
sir.
Perfect. Everything is clear up to this point, right?
Yes, sir.
Okay.
Yes, sir.
As far as evaluation is concerned, I have already shared a document, but I may change that evaluation policy a little bit, because keeping in mind that this is going to be completely online, and also we are yet to decide how the exams will be conducted in the coming semester. So we'll come there later on. Okay. So let us start from here actually. Okay. So what is the goal of this course? What is the goal of high performance computing? So, in one sentence, the goal of high performance computing is to achieve the maximum possible performance out of a particular system for a particular problem. So, let's first look into the keywords. What are the important keywords here? So, the first keyword which you can see is like performance. Okay. The second keyword I can see is the system, and the third keyword we can see is like a problem. Okay, so once again it's very important to really understand this definition. So the goal is to achieve maximum possible performance out of a particular system, okay, for a particular problem. Now let's look into the first keyword, which is performance. Which is performance. Now performance is basically related to time here actually. I mean, whenever you try to measure the performance of anything, a machine or whatever, basically it's a quantitative measure. You can really measure it actually. So it is typically, I mean, generally it is related with time. Okay, so it is almost like how much work you can do per unit of time. That's what a performance in a very abstract way. I mean, we'll get into the deep meaning of performance in the perspective of computer science, but overall a very brief or abstract idea is like performance is something which is related to time and how much work we can do per unit of time. So it is almost like some kind of a rate actually, rate of doing something. So that's typically is performance. The second keyword is the system. Okay, so system is basically your machine, the architecture, the architecture. Okay, now so basically your computer, your machine, computing system actually. So that is that system we are talking about here. Now the most important aspect of this system is that it is non-deterministic in nature. Okay, I will come to this point again. So the system here is a system which is non-deterministic in nature. Non-deterministic in nature. Okay, just keep this point with you. We'll go there again. I mean, why it is non-deterministic in nature. And the third one is basically the problem. So that is a particular problem. So that's the third keyword. So that is the problem. So the problem is basically the algorithm. Whatever algorithm you are working with, or it can be in a more broad sense, it can be an application. Okay, yes. So the point is we need to understand it as a whole and not in parts. So that's the most important I mean takeaway, that need to understand uh, as a whole. I mean, as a whole, not in parts. Okay, why I am telling this, because typically what happens till now, if you have not done a HPC course, so you do a computer architecture course. So it's a, I mean, it's a independent course. I mean, the goal is to really learn about computer architecture, or you do a programming course, or you do a algorithm analysis course. So when you are doing an architecture course, you are not too much I mean, interested in which algorithms you are going to run on that architecture. When you are doing an algorithm course or you are doing a serial programming, you are not always very much interested in on which system I'm running my application, because you're not really interested in performance per se. I mean, till now maybe. So now the objective has changed actually. The objective is like you have to care about the performance, what you are supposed to get from a system for a particular problem. So you have to look everything as a whole and not in parts. That's very, very important message actually. We have to learn that actually, how to look into everything as a whole and not in parts. So now the question is, what is expected from a good programmer? Okay, in the present context actually. So till now, what is expected if you have not done uh, a HPC or a parallel programming course? So generally, what is expected from a good programmer is accuracy. So whether you are able to write a code which can give you correct answer, um, correct acceptable answer. Okay, so basically you are more concerned about the correctness actually, so accuracy, correctness. Okay, I mean it depends from problem to problem, right? I mean sometimes like I mean we can use an adjective to this accuracy, like it is very accurate, it is not so accurate, depends on what problem. Now if you're adding two numbers, let's say 5 plus 5 is equal to 10, you cannot say 5 plus 5 is equal to 9.5. So there the correct answer is only 10. But then there are problems where like it depends on a lot of parameters, like there is some kind of acceptable accuracy, like it is close to the real answer but not really the ideal answer, because sometimes what happens, if you want to get more accurate answer, you need to do more computations. I will explain that part. So typically in accuracy, you test your code in several ways. You test on corner cases, you test on boundary cases, and you make sure that your code or program is acceptable and it works for all kinds of situations. Now, in addition to accuracy, you are supposed to address another issue, and that is related to performance. So now it's the second point is efficiency. Efficiency. Okay. So basically, this is again related to performance, how fast you can do a job. So you can see it's some way related to time. Okay. So these are the two important things which are expected from a good programmer, that he should be able to develop an accurate code. Not only accurate, it has to be efficient. So it should be very, very good in giving the right answer, correct answer in the least amount of time. Okay. Now, why I say accuracy is sometimes proportional to number of computations. So let's say let's talk about a problem, let's say weather prediction. Now weather prediction can be done with some level of accuracy. If you desire more accurate answers, you have to do more and more calculations. Okay, so that's the point I'm trying to make, that these two things are interrelated actually. This accuracy is sometimes proportional to number of computations. So accuracy is proportional in many problems, actually is proportional to number of computations you want to do, number of computations. So it's almost like, let's say you want to integrate a function, whatever function. I mean, let's say you want to find the area under this curve, and if you've done numerical problems, let's say trapezoidal rule, then it depends how many, what is your discretization scheme. So if you do a very, very fine discretization, you have to do more computations, and that will lead to more accuracy. But on the other hand, if you need more accuracy, it will require more time. Okay. Now, if you talk about the weather prediction problem, so there are two challenges. One is you want an accurate answer, and the second is you want that answer within a given time. Actually, there is a time constant. So it's like, I want to predict tomorrow's weather. I need to do it today itself, because the prediction is of no value if I do that prediction day after tomorrow. Okay, so the point is, now you can understand why this is also expected from a good programmer, that he should develop a code which should be very efficient. I mean, which should give you answers, accurate answers within a given amount of time. And that is that, because sometimes That is very, very valuable, because I need the answers on real time, sometime on real time actually, sometimes within a given time constant. So I need the answer in, let's say, 2 3 hours, so you give me the answer. And that tells us that why HPC is so important, particularly in I mean today's context, where we are uh, getting more into data driven problems, we are getting into machine learning and all those things. So there, all these problems involves lot of computations. Okay, and so the only way to do that is by using some parallel programming techniques. And whatever we learn in that, in this particular course, this can be applied to GPUs also. I mean, the basic concepts which you learn, with a little bit of additional knowledge, you can apply that to GPU programming as also. Okay, so this part is clear up to this point, whatever I have discussed.
Yes.
Okay, perfect. So the goal is, you have to evaluate the program whatever you develop in a given software hardware setting actually. So you cannot ignore this part now. So I give you a machine, and you have to get best out of that machine. So that is why this is the definition of HPC, that to achieve maximum possible performance out of a particular system, the system which is provided to you for a particular problem. So if we really want to do that, I need to understand some of the hardware issues, but with a different angle, not really that conventional angle of computer architecture. So that perspective we have to we have to actually learn in this course, like what are the important aspects I should know when I'm looking at a hardware actually, because everything is not important. So that is those brief things we are going to discuss in this course. Okay, now the next point is, this is a very, very important point actually, thinking in serial and thinking in parallel. So this is more about the algorithm design. So I will write it here. Algorithm design. Okay. When it comes to thinking in serial, somehow our brain is designed to think in this way. I mean, it's not very challenging to thinking in serial. And particularly if you have been programming, it's not at all. I mean, because you have been doing this kind of thinking over a long period of time. But when it comes to thinking in parallel, it's challenging, and we'll see how the challenges actually increase as you increase the complexity of the problem. So let's say I take a very simple day-to-day example. Let's say I have a road. I have a road. Okay, and I want to sweep that road. Okay, I want to sweep that road within some time. So what you can do is, like, you can hire one person who can sweep this road, and then I mean, that person can decide a strategy. So the strategy may be like, you sweep it like this, and then you complete the job. So that's how you can sweep it. Or you can come up with some other strategy. You can say that, I'm going to sweep it like this, then I'm going to sweep it like this, and then like this, and whatever. So the point is, if you have to visualize it like from an algorithm perspective, basically you are doing some kind of for loop. So you are gradually sweeping the road. I mean, you can decide, I mean, how you want to travel in this road. Let's say this is a 1 kilometer road which we want to sweep, and there is one person. So that person can decide the strategy, and then that person can sweep this road. What is required as far as resource is concerned? As far as resource is concerned, I mean, some sweeping tool is required. That's all. Okay. Now I want to do the same problem parallelly. So let me draw the same road here, 1 kilometer road. Okay. Now I decide that instead of one person, I will employ 5 person. Okay. Now let us look into as a manager, what are the important decisions I have to take. So the first decision I have to take is, like, I need to break this whole problem in such a way that every person gets equal amount of work. So if I have a 1 kilometer road, every person should get 200 meters of work. I mean, sweeping 200 meters. So the first problem is like problem decomposition, proper problem decomposition, problem decomposition. Okay, so that's the first problem. Now, if I make a mistake here, so say I assign, let's say by chance I make a mistake and I assign 500 meter to a particular person and the rest 500 meter to other four persons, then there is a problem. So that is called load imbalance. So one person will be because the whole sweeping time will increase just because there is a problem in work assignment. Okay, so the point is there should be an ideal problem decomposition. Ideal problem decomposition. So like this one. So this is part one, part two, part three, part four, and then part five. Ideally, each 200 meters. Okay, that's the first point. Second point, what I have to ensure is that I have 5 tools now. I cannot just work with one sweeping tool, because if I just have one sweeping tool, then again the same time will be taken. So if it takes 1 hour here, or let's say it takes 5 hours here, ideally I can do it in 1 hour. If I have 5 persons, ideally they should take 1 hour, but only if I do a proper problem decomposition and I have 5 sweeping tools. So resource, I require resource for every person. Okay. Now, once these two broad criteria are satisfied, given everything is perfect, it's a perfect word, then probably you can do it in 1 hour. So it's a simple school level problem. One person takes 5 hours, 5 persons takes 1 hour. Not much challenging. You simply do a good problem decomposition and you just provide the required resources to all persons. So that's the first level of thinking in parallel. So I can extend this idea to adding n numbers. Okay, I can just extend the same idea to adding n numbers. Okay, so here what you are doing is like you just want to have a for loop for I is equal to 1 to n, and then you do a end, and then it will be calculated one by one. So it is almost like sweeping a road. One by one you are adding 1 plus 2, so it is like this. One by one you are adding those numbers. Here what you have to do, if you have n numbers, so first you divide those n numbers into 5 parts, n by 5. So let's say n by 5 numbers goes here, the next n by 5 goes here, next n by 5. Then each person adds that 1/5 of number. So let's say there are total 1000 numbers. Let's assume there are total 1000 numbers. So the first person will add 200 numbers, the second person will add 200 numbers, the third person another 200, fourth person another 200, and the fifth person another 200. But here again it is little different from this road sweeping problem, because after everybody has added their own part, they are just getting partial answers. So if I have, let's say, first person, it adding for I is equal to 1 to 200. So that is for first person. So he will get a partial answer here. He will get a partial answer. Similarly, the second person can do for I is equal to 201 to 400. He will again get a partial answer. Okay, and so on. And then finally, you have to add all those partial answers to get the final answer. Okay, so up to this point, it is clear.
Yes, sir.
Yeah. Any question at this point? Can you go to the next point? Okay. So these are like simple parallel problems. We typically call them embarrassingly parallel problems. So you just don't have to think too much. Simply just address these two issues and you are done. I mean, you just figure out a proper problem decomposition scheme. You make sure that you have resources available to work on each of these part simultaneously. That's the important point. So if you have divided the problem into 5 parts, you must work on all the 5 parts simultaneously. You cannot work on those parts one by one. Then it's not going to give you this ideal time actually. Okay, now let's think about a more complex situation actually. So I'm going to give you a more complex situation. Let's say I have to dig a hole 1 meter in diameter and 1 meter deep. Okay. Now, as far as serial algorithm is concerned, no problem. I mean, one person can decide his strategy. That person can decide how to dig this hole. I mean, one by one, he can create layers and gradually he can increase the, depth of this hole. Now, think about employing more than 5 persons in digging a hole. Okay, so 5 persons. 5 persons digging the same hole actually. The problem is digging a hole which is 1 meter in diameter and 1 meter in deep. Now instead of one person you want to employ 5 persons. Now what are the challenges you are going to get? Anyone?
Mm,
Uh,
I think
one minute.
means there are two dimensions where we can distribute means if we see it like this. But one, if we distribute among 5% in the depth, then it will be of no use because it will be done in serial way only. But if we
Hmm.
distribute this problem diameter wise, then
Hmm.
it will help, means parallelization will help.
Yeah. So let's understand the answer. So the point is what C has answered is like one strategy is like let's say we have just 5 workers. So I just or let's say we have 6 workers. So I distribute it like that. So I'm talking about digging the first layer actually. Okay, and then there are 6 persons are working. P1, P2, persons and processor. I mean, you can just interchange them. P1 processor one or person P1. Okay, and so on. But the big problem is coming when you start thinking about this direction actually, this dimension. So the problem is like until I finish the first layer, no one can touch the second layer. So there is something called dependency problem. Okay, so it's like there is a lot of dependency. Not only that, if I increase the number of processors, let's say instead of 5 processors, if I start giving say 10 processors or let's say 20 processors, then it's going to be very challenging for those persons to really work together in a synchronized fashion. There will be a lot of classes overlap, this that. So now this is a kind of problem which is always very challenging to think from the design perspective. I mean, how do we come up with a design which really bypasses all these issues actually? All of you could get a feel of the challenges in this particular problem.
Yes, sir.
Yes.
Yeah.
Yes.
Yeah, so yes, so this is just to give you a very abstract idea that parallel programming can be very simple for some problems, and for another set of problems it can be very challenging. The challenges are in terms of resource allocation, the challenges are in terms of proper load balancing, the challenges are in terms of synchronization, the challenges are in terms of removing dependency so that there are no workers actually wait for other workers to finish their job, because if there is a dependency, we'll learn more about dependency, but this is a term actually which you have to really learn very nicely, because this is one of the most challenging part of parallel programming, how to remove dependency. I will come there gradually. So this is a brief introduction. So the summary is that now uh, we have to inculcate this habit of thinking in parallel. So this is a new challenge now, because till now we are trained to think in serial. Now we have to think in parallel. Okay. Now let's look into a typical problem. I mean, we can just extend that idea which we just discussed now to this schematic, serial versus parallel. So now let's say I have a problem. This is a problem. So if I have to think serially, so what I should do is like I can break this problem into small instructions. let's say this whole problem is decomposed into n instructions. So this is like t1, t2, and this t1 is basically time to complete this instruction. Time. Okay, so let's say there are n parts. So this problem has n parts, n instructions or n parts. You can think of it like adding n numbers. So I have to do n computations, and each computation takes T1, second computation take T2, third computation take 3, T3, the fourth instruction take T4, and so on. So the total time will depend on the addition of all these numbers T1 to Tn. So that is like this total time here is like, I mean Ti, where I is changing from 1 to n, and that gives you the total time. And only one processor is responsible because you are doing a serial algorithm. So now if I look at it, so break problem, discrete series of instructions. So that's like problem decomposition, serial problem decomposition. You can visualize like a for loop for I is equal to 1 to n. Instructions executed serially or sequentially. One instruction, second instruction, third instruction, and so on. Executed on a single processor because you only have a single processor. You are writing a serial code. And this is again important. Only one instruction at any moment in time. So at any given point of time, so this is my time axis. This is my time axis. At any given point of time, I'm just doing only one instruction. Now, what is the philosophy? What is the philosophy of serial programming? The philosophy is this: improve latency. Improve latency. Okay. Now, what do we really mean by latency? There are many different definitions of latency. So the simplest definition I can think of is like time taken to do one instruction. Okay, so let's say how fast I can do one instruction. If I can design a processor which is very good in doing a job very fast, any given task, only one instruction, then I can reduce the complete time. Okay, so this is like latency, how fast you can do something. Now the latencies are of different types. I mean, there is memory latency, there is compute latency. I will come there later, but the the most important message what I'm going to give is like the philosophy of serial programming is always improve latency, how fast you can complete one instruction. If you can do that, overall time will be reduced. Now let's look into the philosophy of parallel programming, which is not really improving latency, which is something else. So that is what we need to understand. So here what is happening, you have a problem. Again, let's say it has n parts. Let's say this whole problem is, let's say, n parts. So first what you do is like you divide the whole problem into four parts. Let's say you have four processors, 1, 2, 3, and 4. So you have divided into four processors, n by 4, n by 4, n by 4, n by 4. So break problem, discrete parts that can be solved concurrently. Now again, new term here, concurrently. Will come here. I mean, what is concurrency? So basically, simultaneously. So break the problem that can be solved concurrently or simultaneously. But the challenge is every algorithm does not allow you to do that. That's the point actually, that every algorithm does not allow you to do that. I mean, straight away it may not allow you to do that. You have to think if there is a other route to do this actually. So how do you incorporate concurrency in your algorithm? That's another challenge, because you can only break a problem into discrete parts that can be solved concurrently when your design allows you to do that. Otherwise you cannot do this. So let us consider a situation that you have designed the algorithm which allows you to do that. So then I mean, break your problem into four parts, each part again broken down into a series of instructions. So that is similar to this part actually. So now each problem is like an independent problem which can be done sequentially. So each part again broken down to a series of instructions. Each instructions from each part execute simultaneously on several processors. So now you have four processors, 1, 2, 3, 4, and if all the processors are working simultaneously. Now one thing we definitely need to worry about is that overall control or coordination mechanism. So it is almost like 10 workers 10 workers trying to sweep a road, or 10 workers trying to dig a hole. I mean, someone has to coordinate that they are working properly, they are really working on their part. So if you go to the previous example, like let's say this example, now you have asked the person want to just work in this region, but because of some reason the person won't start working on this region, then there is a problem actually. So there has to be some coordination mechanism that restricts that worker to really work on what has been assigned to that person. Sometimes it's very challenging. We'll see. I mean, if you think from a coding perspective. Second is how do we do that problem decomposition so that no one is sitting idle? Everybody is given some task at a given point, because if you look into this problem of digging hole, that's going to be a very difficult situation. I mean, how can you ensure that you have 10% or 20%, and you simultaneously give them work? Because in one direction you are almost dependent in this direction. So unless you finish the first layer, you cannot assign that work to someone else. So if this is let's say this is the 3D view of the whole. Now unless you complete this part, you cannot do assignment of this part here. But if you look into uh, this problem, there's cleaning a road problem. In the very beginning, we were able to divide the whole problem into 4 parts, 5 parts, whatever n parts. But here you cannot actually. You have to finish the first layer, gradually you have to do the second layer, gradually. So gradually you have to go down here. So in algorithms also these kind of challenges come, like you cannot just in the very beginning divide everything and then you are done. That is not going to happen in most of the challenging algorithms. So you need to think about that. Now let's come to this point, that here the philosophy is improved throughput, not latency. Now look into these terms very carefully. Here the philosophy is improved latency, here the philosophy is improved throughput. Latency, the unit of latency is, what should be a unit of latency?
Seconds. I mean, unit of time.
Exactly, units of latency is seconds, units of time. What is the unit of throughput?
In number of instruction per time.
Exactly, it's a rate. It's not time, it's a rate. It's a rate. Okay, how much instruction you can do per unit of time. So you see how different these two philosophies are. So in serial case, you are just interested in how I am going to reduce the total amount of time, how I am going to reduce the total amount of run time, total amount of execution time. So I have to just make sure that I have to improve the latency. Here, it doesn't matter whether how much time, yeah, whether you are taking the least amount of time to complete one instruction, but what matters is that per unit of time, how much amount of work you can do. So here you are trying to improve the rate, here you are trying to improve the absolute unit of time. So that is like the latency, the seconds. Okay, so this part is clear to all of you?
Yes, sir.
Yeah. So this is a very important, I mean, very important questions. I mean, someone can ask if you have done a parallel programming course, like what is the main difference between serial and parallel programming. So one of the main difference is that in serial programming the philosophy is improve latency, whereas in parallel programming the main philosophy is improve throughput. Okay, I hope everybody all of you have understood till this point. Now we can go to the next point. Okay, now as I discussed in the very beginning, we need to develop a systems perspective. Now we need to understand what is the systems perspective, because till now probably you have not done that. I mean, that systems perspective. What is systems perspective? So the point is systems. So that is computing systems are in general non-terminating and non-deterministic in nature. Non-terminating and non-deterministic. Now, what does that mean? What does that mean is like, uh, sometimes you will see that you just ran a code and it does not get executed, a segmentation fault or whatever fault, I mean, for that matter. But when you design an algorithm that is terminating in nature, like if you design an algorithm to add n numbers, add n numbers, okay, now you say that these are my n numbers, 1 2 3 4 and so on. These are my n numbers, I'm going to add it. So I'm just going to add these n numbers, I'm doing an addition. Okay, so in the very beginning you say that it is going to take of the order of n time. Okay, so you are very much deterministic, this is very deterministic in nature. In the very beginning you are saying it is going to take order of n, and you are also saying that it is terminating, that you are 100% sure that this algorithm is going to give you the correct answer. So the algorithms by its nature or by its behavior is terminating, it is deterministic, and it is platform or independent in nature. So when you design an algorithm, you don't take into account whether I am designing that algorithm for Python or for C or for Fortran or for some other language. Okay, but when it comes to the system, all these things come into account. I mean, I can write a code for adding n numbers. It will take different amount of time. If I design that code in C, it will take some other amount of time. If I try to implement it on Python, it will take some other amount of time. If I try to implement it in Fortran, it is not only language dependent, it's operating system dependent as well. I mean, you can run a C code on Windows, you will get some other time. You run it on Linux, you may get some other time. It is dependent on compiler. You use a Intel compiler, you get some other time. You use a GNU compiler, you get some other time. So the point is, we need to keep this perspective now, that why we need to keep this perspective, because the systems are non-terminating in nature, systems are non-deterministic in nature. You take a code, you run it on the same system in the morning and in the evening, you will see that it will take two different amounts of time, even if that's 1-2% different, but there will be different, there will be some difference, guaranteed. So those differences can come because of different nature. I mean, that can be because of the heat in the system or whatever. But when you design an algorithm, in the morning, it is of the order of n. You design the same algorithm in the same fashion in the evening also, it is of the order of n. Okay, so this is deterministic in nature, this is terminating in nature. So when you design an algorithm on pen and paper, you know that you are going to get an answer, it's going to terminate. In case of system, it's not guaranteed, it may just does not get executed, so it is non-terminating in nature. And when it comes to real implementation, it is very much platform dependent in case of real execution. So this part is clear to all of you? This part is clear?
Yes.
Yeah.
Yes.
So the point, the summary, the takeaway point from this discussion is that we need to develop this idea of systems perspective. We need to think it as a whole and not as a part. I mean, I cannot take it, make it design in one way and then system in other way. We need to think in more like a one common perspective. Okay, now let me discuss a little bit about the organization of the parallel platform. So whatever we have discussed till now, let me show you a little bit in a schematic. So if you look into the organization of parallel platforms, it looks something like this. So there is a logical view. Okay, there is a logical view, and then there is a physical view. So that is the system perspective, physical view. Okay, so this is a logical view, this is physical view. So physical view is basically the architecture part, and the logical part is actually how the programmers look into it, because programmers basically use some kind of logic, I mean, while designing that algorithm. So this is more like a programmer's view. Okay, now when when programmer look at it, I mean, particularly from parallel perspective, I'm talking about. Now, programmer has to think about two important aspects. One important aspect is how does the programmer express parallel, or how does the programmer incorporate parallelism in the algorithm. So this is like expressing parallel task. So that's the first aspect the programmer has to think. The second aspect is the mechanism for interaction. So it is like if 10 workers are working on a given problem, let's say road sweeping or whatever, they have to coordinate. Actually, they need to interact with each other, then only they can finish this job. So as a programmer also, when you are working on parallel programming problem, you have to think about this mechanism. Okay, I will write it: mechanism for interaction or communication between tasks. Mechanism for interaction or communication between tasks, and those tasks can be executed on different processors or cores, whatever. We'll go to those details gradually. So the point is simple, that in one hand you have to think about how to express parallelism, how to introduce parallelism into the algorithm, and second, you also have to think about mechanisms for interaction between those tasks. So it is not only about just figuring out how the problem can be decomposed into independent tasks, but you also need to figure out how those tasks are going to interact with each other. Okay, now um, so here actually there are several models. So this is one of the focus of this course actually. So there are several models actually, models to determine models to, I will just write it, models to determine, I will say, the control structure of the program, the control structure of the program. So that we are going to learn gradually. And here actually you have to think about, so here it is more about models to determine the control structure of the program. Here we need to learn about the models of communication between the tasks. Okay, so models of communication. Okay, now when you talk about these tasks, parallel tasks, okay, now this parallel task can be done, I mean, this can be specified, this can be specified at various levels of granularity, at various levels of granularity. Okay, so again I have introduced a new term. I will get into those in details as we go forward in the course. So I already introduced couple of terms actually, like dependency, concurrency. Now the third term is granularity. So granularity is something like how small those tasks will be. Okay, so let's say if I again go back to this example, I mean, let's get back to that road cleaning example. So let's say I mean, you have this road. Okay, you have 5 workers. Either you can go with this design, 1 2 3 4 5, or I can go with this design. So like this, I do it like this: 1 2 3 4 5, again 1 2 3 4 5, and so on. So here you can see that each task is very fine, actually granular, but I'm going to complete the whole job, but it's a different approach. I mean, first I took this part, I allocated all the 5 workers, they worked on small part, and then again I took another part, again allocated 5. So here you can see this is fine granular, this is like a coarse granular. I mean, you have given a big amount of job to each worker. This part is clear? This part is clear to all of you?
Yes, sir.
Okay, perfect. Now, so this is the overall organization of parallel platforms. So let us summarize whatever we have learned till now. So the first thing is the theory of parallel algorithm design or theory of parallel computing is based on abstract concepts of time and memory, which may ignore real life constraints for simplicity and therefore not take into account non-deterministic and hardware factors. Now we can just understand instead of getting into the complexity of the sentence. Now when you say me that you take of the order of n to add n numbers, did you take into account how much time was required to, I mean, just to read the data from memory? Do we take into account that part here? Can anyone answer me this question?
No, sir.
No, sir.
Yes, exactly. So when you do a complexity analysis, I mean typical complexity analysis, you just tell of the order of n, of the order of log n, or whatever, of the order of matrix multiplication, of the order of n cube, but you completely ignore the amount of time which it takes to just to read the data from the memory. So because finally, I mean, in any solution, I mean, solution, it has two components. One is the data component. I mean, you have to read the data and then you have to perform the computation, which is the compute part. Okay, but typically we just focus on this part, and gradually we'll realize in this course that probably this part is more important than this part actually. Okay, that's a very important learning we are going to get in this course actually. So the point is that when you think when you even talk about serial complexity or parallel algorithm design, so there are two models. One model, the basic abstract model, you just take into account this part, which is the compute part, and you completely ignore the memory part. So that's what is written here. It's based on abstract concepts of time and memory. But there are models actually. I don't know, maybe you have done a complexity analysis course where you take both into account, because ideal complexity analysis should be done by taking both into account, the compute part plus the memory part. Okay, so we'll learn that actually how to do that even for serial programs. I mean, how should I really come up with a good complexity analysis? A good analysis is based on both the compute part, complexity of compute part, and the complexity of memory part. And even better complexity analysis is like which takes into account the complexity of the task interaction part when you are talking about parallel design, because in serial programming there is no task interaction involved as such. But in parallel complexity analysis, so there are three things actually what one needs to understand. So I will just write it here. If you're doing a complexity analysis, you have to think about the data, you have to think about the compute part, and you have to think about the communication part. So that is going to give you the overall picture of the total time to get the solution, and that is something which should be compared with the real runtime. This part is clear with all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Okay. Now the second point is like I just mentioned about non-determinism. Now, how does that non-determinism comes into the system? That let us look into that. The performance, again, performance is measured in time. The performance of a computer, I mean, time plays an important role. Performance is not really measured in time; it's a rate actually. I will come there. The performance of a computer program depends on a wide range of factors, like the nature of the algorithm. Like, like here, if you look into this one, let's say again, let us go to that problem. Okay, so here you are doing the same job, cleaning the road, but you can see that the algorithms will be different actually. Here it's a different algorithm, here it's a different, you are doing it very fine. Or here, even if you look into the serial algorithm, either you can go like this, or you can do like this, and you can do this. So it depends. I mean, total amount of time will be different actually in both the cases. Okay, I mean, the complexity may be same actually, because if you're adding n numbers, the complete total amount of work which you'll be doing is of the order of n, but how we are adding those n numbers will determine the total amount of time. Okay, so it depends on the nature of the algorithm, how you have designed that algorithm. So that's the skill of a programmer. I mean, one programmer can write a program for adding n numbers which will take 1 hour. Another programmer can write the same program for adding n numbers which will take, say, let's say 50 minutes, 10 minutes saving just because the way it is designed. It's not because you are doing less amount of computation, but the total computation which is required is always of the order of n. The second part is the machine, because there are several hardware factors. There are memory hierarchy, there is processor, and all those things are there. Compiler optimization, whether when you are compiling your code, whether you are using some flag or not. I mean, what kind of optimizations is automatically being done by the compiler. So those are another things. The runtime environment. Okay, so what is your runtime environment? I mean, the software environment, the input, the measurement methodology itself. Okay, like how we are calculating the time. Okay, so these are the details will come gradually, and their mutual interaction. So we can see that there are several factors which leads to this non-determinism, and we really need to understand that. Okay, so the point is the real world is very different from the idealistic algorithmic world, which is very abstract in nature, which ignores a lot of things actually. Okay, so here in this course our focus will be more on the real side. Actually, we'll do some complexity analysis to understand how the programs are designed, but the focus will be definitely on the time measurement, and really to understand how these parameters which leads to non-determinism plays an important role. So the summary is not just enough to get some speed up, but being able to explain the speed up from systems viewpoint in terms of resources. So it is not just enough to tell that one person took 5 hours and 5% took 4.5 hours. We should be able to explain why 5 persons took 4.5 hours and not 4 hours or not 5 hours. So and that needs a very detailed understanding of the overall computing ecosystem actually, and that is the focus of this course. So do not just take this course as a parallel programming course. That will be a big mistake. We really need to have this systems perspective. Okay, now let me summarize this discussion, whatever we have done till now. So this is called a parallel programming map. So this is taken from a paper, journal paper, journal or conference, I don't remember, but this is taken from a paper, this map, parallel programming map. Now it almost looks like a graph with nodes and edges. Okay, now let's look into this actually. Very interesting this is. So you can see you have parallelism. Now you need both. You need a software side, you need a hardware side. So you can take any of this direction. So in the hardware side, we need to understand how the serial processor works itself. I mean, how the serial codes work actually. So that is how the first thing we need to understand. Then we need to understand what are these two kinds of system. What is the shared memory system? What is the distributed memory system? Okay, how they are different. And then so shared memory is basically the multi-core system. So you have one processor, you have several cores. And then distributed memory is like you have multi-processors, and inside each processor you can have several cores. We'll come to that gradually. And then this cache is very important, which is going to play a very important role in our course. So this is one side. So ideally, generally what we'll do is like first we'll complete this part. It will not take more than 3-4 lectures, and then we'll go to this part actually. I mean, one can travel in any direction, but I prefer doing this part first, this hardware part, because then it gets connected here. And then what we need to understand here, we need to understand a lot of things: concurrency, the design of algorithms, the decomposition techniques, concurrency control, resource management, synchronization. There are a lot of issues in synchronization like mutual exclusion, atomicity, deadlock. And as far as the memory is concerned, there are techniques which you need to learn, like privatization, private variables, and all those locality, I mean, temporal, spatial, all those things we need to understand the locality. Okay, then as we go down, we need to understand how to remove deadlock and all those things. And of course, some of the other important things like scheduling, um, synchronization, and all those things. Yeah, so this gives you us a overall understanding that what we are really going to do in this course for the next couple of months, and gradually we are going to take case studies um, to really understand how to apply these concepts here. So before we end, we have some more time, so I would like to discuss one important concept. Okay, so this is the first module actually. This is the these are the important topics which are going to cover in the first module. So we are going to take a modular approach in this course. So the first module will be focused on the hardware perspective, but again looking at the hardware from a programmer's perspective, not a typical hardware perspective. And then gradually we'll go into some of the important serial code details actually, like serial code optimization and data access, how to improve data access, balance, and all those things. Dependence, what is dependence testing, loop fusion, loop distribution. We'll go there gradually. So let's end this lecture by a very important concept, that is, what is performance? How do we measure performance? Okay, so what is the quantitative measure of this performance? So let's first look into the architecture side of the story. So let's say I give you an architecture and I ask you what best performance it can give you. Okay, so let's go to the next slide. Okay, so the measure of compute performance, so in this HPC, this P is actually in the middle, performance, and then there is adjective which is high. Okay, so this adjective can be low, high, whatever. Now we have to understand under what circumstances this adjective can become high. Okay, now let's first understand what is the measure of this compute performance. So typically it is measured in flops, so that is floating point operations per second. Okay, now whenever you calculate something, you need some other quantities to calculate that performance. So what are the important quantities we need to calculate the performance? The first thing which we need is the clock rate. That is the first thing which we need. So that is like if you see, tell that 2.5 gigahertz processor, that gives you the first important information. The second information which is need is how many flops you can do per cycle. Okay, so what is the unit of clock rate? Can someone tell me? Clock rate is given in what unit?
1/second.
No, not 1/second.
Frequency.
Okay, I will extract that answer from you, don't worry. Okay, now we'll go there. So let us first discuss the important three quantities. So the first quantity is clock rate, the second quantity is flops per cycle, and the third quantity is number of cores. So this is unitless, number of cores. Okay, now this is flops per cycle. This is the second quantity is flops per cycle. Okay, and then you have a clock rate here, which has to be something which will decide what is that, and the final answer which you are going to get is flops actually, because that is what is the performance, flops. Okay, so what should be ideally, what should be clock rate? We should express it in what?
Cycle.
Yeah, number of
Cycles.
number of cycles
per second.
Exactly, number of cycles
Cycle
per second.
seconds.
Yeah, so because then cycle will cancel and I will get back flops per second, because that is what I'm looking for, floating point operations per second. Okay, so now we know that this 2.5 gigahertz, that is nothing but this is cycles per second. So when you multiply cycles per second with flops per cycle, so that is like how much this microprocessor can do actually. So today's microprocessors typically do 4 flops per cycle, 4 flops per clock cycle. So that number will come here, and number of cores is a unitless number. So if we put these three numbers here, we'll get the ideal theoretical performance. So let's say these numbers are given. Let's say you have a single core, only one core, 2.5 gigahertz processor. Okay, so let us multiply these three numbers. So the first number is 2.5 giga. So I have to write 2.5 into 10 to the power 9 cycles per second. Okay, so this is cycles per second. Second number is, we know today's architecture can do 4 flops per clock cycle. So I will write 4 flop per cycle. And then I have only one processor, which is single core. So I will just put one core here. So cycle will cancel and I'll get 4 into 2.5. So that is 10 and 10 to the power 9. So that will become 10 gigaflops. Now you can see 10 gigaflops here. Okay. Now suppose typically in your laptop, it is a quad core processor. So you have 4 cores. So ideally your laptop can give you theoretically 40 gigaflops. Now, how much you can extract from that, that is your responsibility. So sometimes you will realize that your laptop can give you 40 gigaflops, but you are not even able to extract 1 gigaflops from the system, just because you are not writing your code in that way, the way it is supposed to be written. So the main point is like each architecture has some theoretical performance, that is the ideal best performance it can give. Now as a programmer, it is our responsibility how close we can go to this best what an architecture can give us. Okay, so aggregating computer power in such a way that delivers much higher performance than a typical desktop computer to solve large problems. So that is when this adjective becomes high. So your typical desktop or your typical laptops, just now we calculated, it gives you around 40 gigaflops. If you have 4 cores, then it will give you 40 gigaflops. So if you can make a system which can give you much higher than 40 gigaflops, so that is when you can say that's a high performance computer. This part is clear to all of you?
Yes.
Yes, yes.
Yes.
Yeah. So this part, all of you should put it in your head for the rest of the course. This calculation, you should never forget that how do we measure performance. So the first thing is the frequency, this clock rate, which comes from this quantity, which we all know that whenever we talk about the processor, we typically talk about 2.5 3.5 gigahertz, not beyond that, otherwise your processor will get burned. So typically in gigahertz range. Then this is a number which is standard more or less, that typically it gives you 4 flops per clock cycle. And then you have number of cores, actually number of cores, like how many cores, like today it's very common to even have like 6 cores per processor, even 12 cores, and then there are very sophisticated processors which has like 64 cores per processor. So you have only one processor which has 64 cores. And if you see and look into the GPUs, actually, so the only advantage which GPUs has is like these numbers in thousands, actually. So typically a GPU has thousands of cores, actually, and the clock rate is still in gigahertz. So now we can imagine why GPUs are getting so popular, actually, because they have I mean a significantly higher number of cores in a graphics processing unit. You have thousands, the cores are in thousands. Although it has some limitations, I mean that is not a part of this course. Maybe in the end, if you have time, we can discuss. But you can more or less take this formula as a pretty standard formula to understand what a system which has been given to us can deliver to us, and how we can design a code which can extract maximum out of this system. And that is why in the very beginning I wrote that the goal of HPC is to achieve the maximum possible performance out of a particular system for a particular problem. So the moment you sit into a system, the first thing we have to understand is that how much how capable that system is. So we'll learn that how to extract that information from your system. I mean, on Linux we can just look into that. I mean, how we can extract that information, and then we can see whatever codes you are designing, how close that code is in terms of giving performance to that ideal theoretical performance, because this number is actually theoretical. As I told you, this number is theoretical performance, ideal. So it is always very difficult to write a code which will go very close to this performance. Okay, so I think we can end this lecture today. If you have any questions, we can ask.